Now let's look at the principles involved in drawing actual ladder diagrams. And first of all, why is it called a ladder diagram? And this is actually a question in your worksheet. It's called a ladder diagram because it looks like a ladder. The power lines are vertical. There's one on each side, and they look like the legs of a ladder. All the controls and loads are horizontal, one by one, and they look like rungs of a ladder. This diagram shows logic. These are actual logic circuits, if you want to think of them that way. And in fact, many engineers, electrical engineers, study logic, and they make drawings of logic diagrams. And if you look in some electrical textbooks, you'll see people will draw a ladder diagram here and a logic diagram here representing the same circuit. The whole point of a ladder diagram is that although we've got a real complicated thing here with many wires going every which way, this diagram breaks it all down to its simple logic and makes it easy to understand. And what we need to remember is that a ladder diagram is not to scale in any way at all, and it's not representational. It just shows functions and connections. So it looks like these switches are really close together with really short wires. They might be 100 feet apart. You can't tell from this diagram whether they are or they aren't. And here's a start-stop station with a real long wire, just to illustrate the point. So a ladder diagram just shows function and not sizes or locations. In contrast, a wiring diagram does show actual pieces of things because an electrician might use this diagram to connect wires, and so he or she needs to know what gets connected where. But a ladder diagram just shows the function. Another principle is that all the components are drawn in what is called in a state of rest. That is, what state would they be in if the electricity were not connected? Some switches and controls are normally open if there's no electricity. Others are normally closed if there's no electricity. So here at the top of this slide, we see a plain switch, a single pole, single throw, might call it a knife switch, that is normally open, and you know that because that's the way it's drawn. Here is a push button, a start switch, and it's normally open, and you can tell that because it's floating in the air up above the contacts. And then at A up here at the top, there are some contacts. Those are normally open contacts, and you can tell because there's an airspace between them and they're standing open. Now look at the drawing at the bottom of the screen. Here is a stop push button. You can tell that it's a normally closed switch because here it's drawn in its resting position and its contacts are making a complete circuit there. Then these contacts labeled T are normally closed. This is the symbol for contacts, and the diagonal line is a symbol for normally closed contacts. When you draw this diagram, you show the steps that this circuit will follow in order from top to bottom, beginning with the power coming in off the line, going through the step-down transformer, and then one by one through each of these rungs of the ladder, controlling various steps along the way. Another principle, we always draw input on the left and output on the right. So input could be something like a switch. We always draw our start-stop switches on the left, our auxiliary contacts on the left, And we always draw loads on the right. So it could be a starter coil, could be a light. We draw only one load per line, and here are the lines. L1 is on the left and L2 is the leg on the right, and in between go these rungs of the ladder. Each one is a line with only one load on it. So here's a motor coil, a relay coil, a light, an alarm, and the loads always go directly to L2, which is the neutral. Remember, this is a 120 volt control circuit. The loads always go directly to L2, except for the motor starter coil, which has to go through overload contacts before it gets to L2. The controls always go between L1, this vertical left line, and whatever the load is. And each line has to have at least one control device. And it might be contacts from the control relay, it might be a switch, it might be a float switch or a temperature switch, some kind of control. Now we number everything so that our electrician can keep track of what's happening. The vertical legs of the ladder are the power lines, and they are always numbered L1 on the left and L2 on the right. We number each line in the control circuit, 1, 2, 3, starting at the top and going down. In addition, we put a number for each conductor, and conductor means piece of wire. This is very useful for the electrician who's installing things, doing the wiring, or if they're coming along later doing some troubleshooting, trying to figure out why something isn't working right. These numbers are invaluable. And by the way, this is a question in our worksheet. Why do we number the conductors? So, let's say a conductor comes from L1 to one side of this push button switch. Then a wire comes from the other side of the push button switch over to another push button switch. Well, that's a different piece of wire, so it gets a different wire number. Meanwhile, our electrician gets these are purchased wire number labels. Our electrician puts that same number on that wire using your ladder diagram and your numbers. The actual wires match those numbers. So now, if somebody has to come along later and troubleshoot, they can follow exactly what wire is going where. And so here is, again, an old, you can tell this is an old one. This had 460 volt, 115 volt, so slightly newer than our oldest old. Anyway, here is a diagram, a ladder diagram out of an electrical book with the various components labeled. And I've highlighted them in yellow to make them easier to see. Now, when you're drawing a ladder diagram, remember, we already talked about this, but we are not drawing anything to scale. We are just showing the function of the circuits. And we are always drawing our switches and our contacts in resting position. Either they're normally open or they're normally closed. All right, so other guidelines. For the most part, these lines are all horizontal or vertical, except for you can see a few exceptions connecting to the motor and connecting to the transformer. But the other lines have vertical lines and horizontal lines. And we always use continuous lines, no dashes or phantoms or hiddens, continuous lines. And then where a connection occurs, we make a dot. So you can see where these lines from the transformer connect to the line voltage, there's a dot there showing which line is connected to what. When there's not a dot, that means that's not a connection. So this line from the left side of the transformer connects to L1. It does not connect to L2 nor L3, and you can tell that because there are no dots there. Then down in the control circuit, you see dots here for each of these connections. I will say that if there's a T connection, as you see in most of these rungs connecting to legs of ladders, you're not actually required to put a dot there because there's nothing else that could be but a connection. So it's nice that they put dots here. They're not 100% required. But up here on the line connection, they are required because you have to show what connects. Then general guidelines that apply to any professional drawing. We try to keep a clean and uniform looking drawing. So we want to figure out how can we have the fewest number of lines, how can we have the fewest lines crossing other lines. Insofar as possible, can we align things? So for example, on the line, the power lines, notice how these three fuses are lined up. Down in the control circuit, notice how these three switches are lined up. And it would be good if these coils could line up also. And then just think about white space. And white space means space on the page or on the drawing where there are no lines or symbols or text. White space is just this open white area. And we want to try to keep the amount of white space balanced. So evenly spaced lines, evenly distributed white space. Now here's our assignment. Good old textbook author, he's done it again. So here's the part of a ladder diagram that he provides, and what we are going to do is basically just copy this. I know there's some things missing. Don't worry about it. Just copy this drawing. With one exception, I would recommend, and you don't have to do this, but don't you think that it looks better to get our motor circuit over here on the right side of the transformer? As you see in this drawing on slide 20, here's the transformer in the middle, here's the motor circuit over here on the right. That lets your ladder rungs be straight and horizontal. The way he's done it here, he's got what you call a dog leg, a zigzag corner in his ladder. That's not a ladder, that's a zigzag. So I recommend you make one change and draw your motor stuff over here on the right hand side of the transformer. That will let you stretch out this rung of the ladder in a good looking way. And then we're not going to put every darn thing in this control circuit. We'll draw this much so we can kind of get practice showing them. I actually just draw my own thingies, which is probably stupid, but I do. There is reputed to be a set of electrical symbols as blocks stored in AutoCAD's Design Center, and I confess to you I've never used that in my life. They keep moving it around and it keeps changing, and but if you would like to use that in the current revision of AutoCAD, I think it's under the View tab. There's a thing called Palettes and you can get to Design Center. I might be wrong, but I think that's where they've put it. Or you can type in the command line ADC, and I think that will bring up the Design Center. So you can fool around with that if you would like. There are also CAD blocks available online, or as I say, you can simply draw your own and use any title block you like.